Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 9 on time series modeling and forecasting. In this lecture, I will discuss the stationary processes. Before that, in the last lecture, actually we have discussed various measures connected with the time series, like mean function, variance function, auto-covariance function, auto-correlation function, and partial auto-correlation function. So, first I will present some results in connected with the partial auto-correlation function, and then we will come to the stationarity of the process. So, we will discuss the stationarity of the process. Now, suppose y t is a time series, and we assume that the mean of y t is 0, expectation of y t is 0. Then the partial autocorrelation function of order k is the value of the last coefficient a k k that minimizes eta equal to expectation of y t minus summation I equal to 1 to k a k I y t minus I whole square. So, if you minimize the expectation of square of this quantity, actually here you have a linear combination of past values of y t, means y t minus 1, y t minus 2, so on y t minus k. So, basically you are minimizing. So, if you consider the regression between y t and the past k values of y t, if you run the regression between y t and these past k values, and you minimize the residual sum of square, then partial auto-correlation function of order k is actually the last coefficient a k k. So, we prove this result. Without loss of generality, we assume that sigma square y is equal to 1. Again we introduce some matrix and vector notations. So, we write z k minus 1 equal to y t minus 1, y t minus 2, so on y t minus k plus 1 transpose. So, this is actually k minus 1 cross 1 vector, then alpha transpose is equal to, so alpha is equal to a k 1, a k 2, so on a k k minus 1 transpose. Then we have eta equal to expectation of y t minus summation I equal to 1 to k k I y t k minus I square equal to expectation of y t minus, you take first k minus 1 terms and then you have the last term akk yt minus k whole square, which is equal to expectation of yt minus alpha transpose zk minus 1 minus akk yt minus k square. And then we take the square of this quantity and then expectation. So, expectation of yt square is equal to 1. The expectation of alpha transpose zk minus 1, zk minus 1 transpose alpha is equal to alpha transpose pk minus 1 alpha. The expectation of this square of this term is akk square, expectation of yt minus k square, and expectation of yt minus k square is equal to 1. Then we get the cross product terms. So, minus 2 alpha transpose expectation of yt zk minus 1, which is equal to rho k minus 1, minus 2 times akk expectation of yt minus k is equal to rho k, and then you have plus 2 times akk alpha transpose zk minus 1 yt minus k expectation of this quantity, which is rho star k minus 1. So, basically you have to minimize this expression with respect to alpha and alpha kk. For this purpose, we differentiate eta with respect to alpha and alpha kk, and then we substitute it equal to 0. So, first we differentiate with respect to alpha. So, if you differentiate the first term with respect to alpha, you get 2 times pk minus 1 alpha. Then the differential coefficient of this term is 0, this term appears, and if you differentiate it with respect to alpha, you get minus 2 times rho k minus 1, and then you get this term plus 2 times akk rho star k minus 1, and then 2 you take common, and then you move towards the right hand side. So, ultimately you get this equation, and from here you obtain alpha equal to pk minus 1 inverse rho k minus 1 minus akk rho star k minus 1. So, you get this expression for alpha. Again we differentiate eta with respect to akk. So, the differential coefficient of first two terms is 0. Here you get 2 times akk, then you have this term which involves akk, you get minus 2 times rho k plus 2 times alpha transpose rho star k minus 1. So, again you take 2 common and move towards the right hand side. You finally get this equation, and in this equation we replace alpha transpose or alpha by this value. Now, you can solve this equation for akk. So, you get this equation and you solve this equation for akk, which gives you akk equal to rho k minus 1 transpose pk minus 1 inverse rho star k minus 1 divided by, in fact, in the denominator you obtain 1 minus rho star k minus 1 transpose pk minus 1 inverse rho star k minus 1, but these two quantities are equal. So, we replace it by rho k minus 1 transpose p k minus 1 inverse rho k minus 1. Now, this is the same expression as for the partial autocorrelation function of lag k, which we have derived in the last lecture. Hence, we obtain the result. Now, since the expression for the partial autocorrelation function involves inverting the matrix P k, which is usually very time consuming, particularly when k is large. So, for obtaining partial autocorrelation function, one can use Durbin-Davidson algorithm, which obtains the partial autocorrelation function recursively. So, in this expression for partial autocorrelation function, we just replace rho k minus 1 transpose p k minus 1 inverse by alpha k minus 1 transpose by this expression of alpha k minus 1. And the denominator also, you replace this term by alpha k minus 1 transpose. Or in the summation form, you can write it as which is equal to rho k minus summation j equal to 1 to k minus 1 a k minus 1 j rho k minus j divided by 1 minus summation j equal to 1 to k minus 1 a k minus 1 j rho j. Now, a k minus 1 j is the jth element of alpha k minus 1. Further, alpha is equal to p k minus 1 inverse rho k minus 1 minus a k k p k minus 1 inverse rho star k minus 1. So, you can write it equal to alpha k minus 1 minus a k k alpha star k minus 1, where alpha star k minus 1 is obtained by writing the elements of alpha k minus 1 in reverse order. Remember that the difference between rho star k minus 1 and rho k minus 1 is that in rho star k minus 1, you have written the elements of rho k minus 1 in reverse order. Similarly, you can obtain alpha star k minus 1 by writing the elements of alpha k minus 1 in reverse order. You can write this equation in a scalar form as you have the vector a k 1, a k 2, so on a k k minus 1 equal to a k minus 1 1, so on a k minus 1 k minus 1 minus a k k a k minus 1 k minus 1, so on a k minus 1 1. Now, this is how you can calculate different quantities and partial autocorrelation function recursively. And you can also apply this algorithm for calculating the sample partial autocorrelation function. What you have to do is just replace the parameters by their corresponding sample quantities. Now, we define purely random process or the random shocks. A discrete process u t, t belongs to capital T, is called a purely random process if the random variables u t are the sequence of identically independently distributed random variables and the process has constant mean and variance. And since it is a sequence of independently distributed random variables, so the covariances are 0, gamma k are 0 for all k equal to plus minus 1 plus minus 2, so on. This process is also known as random shocks. It is also known as white noise process, because if you look at the spectrum of this process, it has a uniform spectrum which is just like that of a white light, although I have not so far covered the spectrum analysis of a process, but we will come to this topic. We will discuss this topic in detail in a lecture on frequency domain analysis. So, in that lecture, the spectrum of then purely random process is uniform, and it is just like the spectrum of a white light. So, that is why it is also called a white noise process. Now, a purely random process is useful as a constituent of other complicated processes. Now, you define Gaussian white noise process or Gaussian random shocks. A process u t, t belongs to capital T, is called a Gaussian white noise process if the random variables u t's are the sequence of identically independently distributed random variables, and along with that u t follows a normal distribution, normal 0 sigma square u, and we denote it by u t follows G W N, Gaussian white noise process with mean 0 and variance sigma square u. Here actually I have drawn a sample of size 1000 from a Gaussian white noise process, and I have plotted this sample, and so that you can look how a sample from Gaussian white noise process looks like. Now, we come to the stationary process. Now, remember that in classical inference procedures, you assume that your observations are identically independently distributed. So, all the observations are from the same distribution. Now, in time series, the things are different. You have a family of random variables. You have a family of random variables y t, and for the particular t, y t is a random variable. So, you cannot ensure that all the y t's are from the same distribution. Now, this may create some problems. To ensure that the probabilistic mechanism which has generated the time series do not change over time, you have to ensure that the process is stationary. So, the first objective of stationarity is to ensure that the probability mechanism which has generated your time series, it remains same. The probability mechanism does not change with time. Then the way process changes is predictable. Of course, you will find changes in y t with t, but those changes should be predictable. And once you ensure that the changes are predictable, it becomes possible for you to make predictions based on stationary processes. then it also makes the process much easier to model and investigate. If the process is a stationary process, then you can easily model it, and then you can easily investigate its properties. And then stationarity is also a very important concept for developing several inference and analytical tools. So, for developing different inference procedures and for applying those different inference procedures for analyzing the time series, you require the assumption that your time series is stationary. Now, a time series is said to be strongly or strictly stationary if the joint distribution of y t 1, y t 2, so on y t n is the same as the joint distribution of y t 1 plus k, y t 2 plus k, so on y t n plus k for all n t 1, t 2, so on t n and k. Or in other words, if f t 1, t 2, t n denotes the joint probability density function of y t 1, y t 2, y t n, then the condition for the strong stationarity is that the joint probability density function of y t 1 plus k, y t 2 plus k, so on y t n plus k is the same as the joint distribution of y t 1, y t 2, y t n, and this holds for all n t 1, t 2, t n and k. So, the stationarity condition implies that the joint distribution of y t 1, y t 2, so on y t n does not change if you just shift the entire time series by say k periods. Means you shift this time series to y t 1 plus k, y t 2 plus k, so on y t n plus k, then the joint PDF does not change. Now, if you take n equal to 1, then this implies that the distribution of y t does not change with t, or the distribution of y t is the same for all t. And since the distribution of y t is same for all t, mu t is equal to mu, and sigma square y t is equal to sigma square y for all t. So, your mean function mu t does not depend upon t. So, you can write it equal to mu. Similarly, the variance function sigma square y t does not depend upon t, and we write it equal to sigma square y. Then for n equal to 2, so suppose we write t 1 equal to t and t 2 equal to t plus k, then the joint distribution of y t and y t plus k depends only on the k, means f y t y t plus k. This joint distribution of y t and y t plus k depends upon this lag k. Actually, this is same as f y t dash y t dash plus k for all t t dash. because the process is stationary. So, the joint distribution just depends upon this k. And this implies that the auto covariance function gamma t plus k, which is actually the covariance between y t and y t plus k, depends only on lag k. So, actually what is gamma t plus k? It is expectation of y t minus mu t, y t plus k minus mu t plus k. And since the process is stationary, mu t is equal to mu t plus k is equal to mu. So, you can replace mu t equal by mu t plus k by mu. And the joint distribution of y t and y t plus k does not depend upon t. So, this expectation also does not depend upon t, it just depends upon k, and you can write it equal to gamma k. So, gamma k is the auto covariance function at lag k. Similarly, the auto correlation between y t and y t plus k, rho k is equal to gamma k upon gamma 0. So, this is the auto correlation function. This also does not depend upon t, it depends upon just the lag k. Then a process is called mean stationary if expectation of y t is equal to mu for all t. So, if the mean does not depend upon t, it is independent of t, then the process is called mean stationary. Similarly, the process is called variance stationary if expectation of y t minus mu t square is equal to sigma square y for all t, means the variance of the process does not depend upon t. And the process is called covariance stationary if the covariance between y t and y t plus k is equal to gamma k for all t and k. So, this covariance function, auto covariance function, does not depend upon t. And if a process satisfies all these three conditions, it is mean stationary, variance stationary and covariance stationary, then the process is called second order stationary or weakly stationary, weak stationary process. So, a time series is second order stationary or weakly stationary if its mean and variance are constant and autocovariance function depends only on the lag. Now, if a process is strictly stationary, then we have already shown that it has constant mean, it has constant variance and its auto covariance function just depends upon the lag k. So, the process is second order stationary. So, a strict stationarity implies second order stationarity or weak stationarity, but its converse is not always true, means a process may be second order stationary or weakly stationary, but it may not be strictly stationary. Now, when the joint distribution of y t 1 plus tau, y t 2 plus tau, so on y t n plus tau is a multivariate normal distribution for all n, then the second order stationarity implies strict stationarity. And the reason is that the multivariate normal distribution is characterized by its first two moments, the mean vector and variance covariance matrix. So, if it is a Gaussian process or normal process, then weak stationarity implies strict stationarity. Now, if you consider the auto correlation function of a purely random process, then for a purely random process, rho k is equal to 1 if k is equal to 0, and it is equal to 0 if k is not equal to 0, because for a purely random process, gamma k is equal to sigma square u if k is equal to 0, and this is 0 if k is not equal to 0. So, from here we obtain this result, rho k is equal to 1 if k equal to 0 and 0 if k is not equal to 0. So, obviously, a purely random process is second order stationary, and in fact, it is strictly stationary also, because all the UTs are identically independently distributed. Identically distributed means the distribution of ut is the same as the distribution of ut plus k, and independently distributed means the joint distribution of ut plus k is equal to the marginal distribution of ut into marginal distribution of ut plus k. Now, you can easily verify that the second the purely random process is strictly stationary. Now, this is the autocovariance function, actually sample autocovariance function of a purely random process. We have taken a set of observations from a purely random process, and then we have calculated the sample autocorrelations of different orders, and then we have plotted it. So, this is the graph. So, you can see that after 0, all other autocorrelations are insignificant. Now, we consider some processes and check whether those processes are stationary or not. Now, suppose x follows a Poisson distribution P mu, and ut is a sequence of identically independently distributed random variables with mean 0 and variance sigma square u. So, in fact, ut is a purely random process. Now, we define a process yt as yt equal to x plus ut. Now, since x follows a Poisson distribution with parameter mu, the mean of x is mu, expectation of x is mu, and variance of x is also mu. Now, this shows that expectation of yt is equal to expectation of x plus expectation of ut, which is equal to mu. Further, variance of yt is equal to variance of x plus variance of u t. So, finally, you obtain variance of y t equal to mu plus sigma square u. The autocovariance function gamma k t is also equal to mu, because gamma k, this is equal to expectation of y x plus u t x plus u t plus k. Now, this is equal to expectation of x square, which is mu, then expectation of x into u t plus k. X and u t's are independently distributed, so you get 0. Then expectation of u t x is 0 and expectation of u t plus k for k not equal to 0 is 0. So, gamma k t is equal to mu. So, the process is second order stationary. In fact, you can easily verify that the process is strictly stationary also. Now, we consider another example. We define the process y t as y t equal to summation j equal to 1 to t u j, and here u t is a purely random process which has mean 0 and variance sigma square u. Then we derive the mean, variance and autocovariance function of the process. Obviously, mean of the process is 0. If you take expectation of y t, it is 0, because all the u j's have expectation 0. Then variance of the process, in fact, y t is sum of these t I d random variables, each having variance sigma square u. So, the variance of y t is equal to t times sigma square u. For obtaining the covariance, we have expectation of y t plus k is equal to expectation of summation j equal to 1 to t u j and summation j equal to 1 to t plus k u t u j plus k. Now, in this product you have t terms with u j square, and remaining terms are like u j and u j plus k, k not equal to 0, and those cross product terms have expectation 0. So, this is equal to t times sigma square u. Then you can easily derive the autocorrelation function rho t t plus k, which is equal to t to the power half upon t plus k to the power half. Actually, rho t plus k is equal to t times sigma square u divided by t times sigma square u t plus k times sigma square u whole to the power half, means variance of ut and variance of ut plus k, and then you can simplify it. So, this is equal to t to the power half upon t plus k to the power half. So, the process is mean stationary, but it is not second order stationary. The variance and auto correlation function depend upon t. Now, we consider the process this y t equal to a cos omega t plus phi. Phi follows uniform distribution uniform 0 pi. Now, if you obtain the expectation of y t, then expectation of y t is equal to you take a cos omega t plus phi, multiply it by the PDF of uniform distribution 1 upon pi, and then we integrate over phi. And you can easily find this integral, which is equal to minus 2 a upon pi sin omega t. Now, this is a function of t. So, the process is not mean stationary. In the same process, if phi follows uniform distribution over interval 0 to 2 pi, then expectation of y t becomes 0, because then you have to integrate here from 0 to 2 pi, and integral from 0 to 2 pi cos omega t plus phi d phi is 0. So, the process becomes mean stationary. Again, in this case, if you obtain the variance of the process, then variance is a square upon 2, and auto covariance is 0. So, the process is second order stationary. Again, if a is a random variable having mean 0, the process becomes mean stationary. Now, we consider the process y t equal to a cos theta t plus b sin theta t, where a and b are uncorrelated random variables with mean 0 and variance 1, and theta belongs to the interval minus pi to pi. Then we verify whether this process is second order stationary or not. So, to verify this, first we take expectation of y t. Expectation of y t is equal to expectation of a cos theta t plus expectation of b sin theta t. Now, a and b have mean 0. So, this is obviously equal to 0. So, the process is mean stationary. Next, we consider the variance of the process. So, expectation of y t square, which is gamma 0, is equal to you have variance of a cos square theta t plus variance of b sin square theta t. Again, variance of a is equal to 1. So, you get 1 here, and with 1 you have cos square theta t plus, again variance of b is also equal to 1. So, you get 1 here, then sin square theta t. Now, cos square theta t plus sin square theta t is equal to 1. So, expectation of theta t is expectation of y t square, that is variance of y t, is also independent of t. So, the process is variance stationary. Now, we obtain expectation of yt plus k, which is actually the auto covariance of order k. Then this is equal to expectation of A cos theta t plus B sin theta t into A cos theta t plus k plus B sin theta t plus k. Then here we obtain expectation of A square cos theta t plus k. Then expectation of A square is 1. So, you get cos theta t cos theta t plus k, and then you have A b cos theta t sin theta t plus k, but expectation of A b is equal to 0, because A and B are uncorrelated and both have mean 0. Again you have another term A b cos theta t plus k sin theta t, which also has expectation 0. And then you get a term B square sin theta t plus k. Then expectation of B square is 1. So, ultimately you get sin theta t sin theta t plus k. Now, cos theta t plus k plus sin theta t plus k is equal to cos theta t plus k minus theta t, which is equal to cos theta k. Now, gamma k is equal to cos theta k, and this cos theta k depends upon like k only, it is independent of t, it does not involve t. So, we conclude that the process is second order stationary. Now, we move to the next example. We consider the process y t equal to summation j equal to 1 to k r j cos omega j t plus theta j. Here R j's are IID random variables following normal 0 sigma square. Then we check whether the process is mean stationary or not. So, we take expectation of y t. Expectation of y t is equal to summation over j expectation of R j cos omega j t plus theta j, and expectation of R j is equal to 0. So, you get 0 here. So, the process is mean stationary. Then to check whether the process is variance stationary or not, we take expectation of y t square here. Now, this is equal to summation j equal to 1 to k expectation of R j square cos square omega j t plus theta j. Now, expectation of R j square is equal to sigma square. So, this is equal to sigma square summation j equal to 1 to k cos square omega j t plus theta j. Now, this actually depends upon t. So, the process is not variance stationary. Again, for the second case, if you take theta j following uniform distribution over interval 0 to 2 pi, you can easily verify that the process is mean stationary. If you take expectation of y t, then this is equal to summation j equal to 1 to k r j 1 upon 2 pi integral from minus pi integral from 0 to 2 pi cos omega j t plus theta j and d theta j. You can easily verify that this integral is equal to 0. So, again expectation of y t is equal to 0. So, the process is mean stationary. Now, to verify whether the process is variance stationary or not, I am leaving it as an exercise for you. So, you just try to check whether the process is variance stationary or not. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. You may ask, how do sociologists view religion? Religion is becoming an important issue for our society. Now, sociologists, this is true that sociologists explain one thing in terms of other things of society. So, religion, if you ask sociologists to explain religion, they will explain religion in terms of other things of society like education, economic development. In sociology of religion, there are two major traditions actually. In one tradition, to use language of methodology, in one tradition religion is a dependent variable. In another tradition, religion is an independent variable. What I mean is that in the view of Karl Marx, who said that religion is the opium of the working class, religion is closely associated with contradictions or relations of class in society. Marx believed that as time passes, societies evolve, and this evolution of society is dialectical, like from a classless society to a class society, class formation, and eventually again a classless society will emerge. Karl Marx believed that laws of human behavior or laws of society are specific to stage of development of society and are closely associated with mode of production or tools and techniques of production and ownership of tools and techniques of production. To Karl Marx, who think that a modern society is a capitalist society, religion is the dependent variable which needs to be explained in terms of class relations. And when he says that religion is the opium of the working class, it means that religion is used by the powerful class, the class which owns the means of production, to legitimize their class position or to confuse the workers. Let the workers think that if they are poor, if they are exploited, and if they suffer from various kinds of problems, it is because of their fate or their deeds in the previous births, and not develop the revolutionary consciousness to analyze the real causes of their poverty or exploitation or ill health. This is one view, and religion is the dependent variable, which also means that tomorrow in socialist society or in communist society, if it ever emerges and society becomes classless once again, religion may not exist. Now, according to another view, Max Weber, religion is actually the independent variable that explains emergence of something else, and that something else is the emergence of capitalism. Max Weber said that unlike in the Hindu countries or the Muslim countries or Christian countries where influence of Catholic Christianity was rampant, capitalism, as we understand by capitalist institutions, capitalism could not have developed. It does not mean that people, Hindus or Muslims or Catholic Christians, they were not acquisitive in nature, but there was a difference between them and those influenced by Protestant ethics in certain countries of Western Europe, and the difference was that these people did not use what they earned from their enterprises for comforts or for saving or for security or for status or prestige, but whatever they earned from their enterprise, they further invested this in the enterprise itself, and they lived simple life. By living simple life and spending the earnings back in the enterprise leads to emergence of capitalism in Western Europe. Here you see that religion is the cause. So, at some point of time, some philosopher, his name was Calvin, who gave a new turn to Christianity and propounded the philosophy of a new philosophy of Protestantism, also called Puritanism, the theory of predestination, which created anxiety in people's mind to know whether they are elect or not, whether after their death they will go to hell or heaven. So, this reinvesting in enterprise and not using the profits for their own gains or for their own comforts, this produce capitalist society or industrialization, in simple language industrialization, or this produce economic development first in the countries of Northwest Europe. And another issue which sociology tackles with regard to religion is whether we are secularizing. Now, it has been found that in the Western countries with urbanization, economic development, industrialization, education, democracy, there is a fall in religiosity. But in our country, secularization is defined in a different way, because we are a plural society, and for thousands of years all religions have been juxtaposed in our country. So, we define secularization as a process in which a state maintains equal distance from all the religions, but does not become irreligious state. So, but this kind of definition or this approach of a state obviously is going to raise new issues, new social problems and religious issues, other issues, but this is what it is. So, sociologists of religion will also study this process of tensions in the process of secularization in a plural country like India. Thank you.